chat window there, and then once I call on you, you can go ahead and click enter, and then your question will pop up, and we'll answer those in the order in which they are received. So we'll try to answer as many questions as possible in the time frame that we have allotted for today. But we'll review that again once he's done with his presentation, and then we'll try to get as many questions done as possible. So, okay, with that, I want to introduce Aaron Herridge. He's actually a two-time NASA intern, and part of his work here actually revolved around fluvial geology, and he worked with the NASA ARES program, which is the Astromaterial Research and Exploration Science Group. He's going to tell you a little bit about his work and actually some of his future focuses as he moves through his career, not only as a student, but obviously as a geologist, and then hopefully one day coming back here at NASA full-time and working as part of that team. So with that, we'll go ahead and turn it over to Aaron, and we'll get started.
All right. Hello, everybody. Good to have all of you here with me. It's a pleasure to talk a little bit about one of my passions, Mars geology. And I understand that all of you are looking at keys to exploring Mars, so I'm going to focus on exploring Mars. I'm not just going to give you rock features and things like that. We're going to talk about a human being going to Mars and exploring Mars visually through satellites, sending rovers to Mars. What is it that you can expect to learn based on the things that you can research right now with satellite imagery? So let's go ahead and go into the first slide I've got here, which is a little bit about my background. I've got a degree in environmental geology that I've already graduated with. I'm also working on a second bachelor's degree in physics. I've actually got just 4 classes left on that, so virtually done. Applicant to a PhD program in geophysics, so planning to continue this career. And in terms of research, I have, as Jimmy said, I've done research in Mars fluvial geology. If you don't understand what exactly that entails, the history of water moving across the Martian surface. What can we learn about it based on what we can see today? I've also done some other physics research. I've done a few internships, currently doing a geophysics internship, so that's a little bit about my background. But let's jump right into the planet Mars. That's what you're all interested in. To start with, this may be old information for most of you, but it's good to take a look at this map here. Where Mars sits in the solar system, we know that Mars is past Earth's orbit. We know it's before Jupiter's. We also know that there's an asteroid belt between Mars and Jupiter. But when you look at this map and you just take a look at how the planets are situated, and you look at the different belts that are in the solar system, you might get a better idea of what you're looking at when you look at Mars's history. When you see the craters and the impacts on Mars and you see what layers they're in and what periods of its history they're in, keep this in mind. You have an asteroid belt, for instance, between Mars and Jupiter. Those asteroids, when they're tucked out of their orbit and they move towards the sun's center of mass, obviously they're going to zip past Mars on their way in. And unlike Earth, Mars does not have a protective atmosphere, and Mars doesn't have the large moon Earth does to take the brunt of a lot of those impacts. So when you look at Mars, you're looking at a planet that throughout its history has been an impact-prone planet. And certain periods there will be more impacts or bigger impacts. That's a clue to interpreting the surface of Mars. So let's go ahead and look a little closer at what Mars is made out of. This is the internal structure of Mars. It's similar to Earth in some ways, but very different in others. Like Earth, Mars has a core and a mantle and a crust. That should sound familiar to all of you. It's got a semi-fluidic core, just like Earth does, that's got metallic composition, iron, nickel, and sulfur. And it's also got a silicate mantle. Unlike Earth, the mantle is believed to be largely dormant. And obviously, we have more to learn about what's going on underneath the surface of Mars, but at this time, what we understand is that it doesn't have a convecting fluidic type mantle like Earth largely has. So while the core has that semi-fluidic nature, not so much the mantle. That has a lot of impact on the features that Mars has on its surface and the processes going on the surface. So it's very important to your exploration to understand that. The crust in Mars is thicker than Earth's. Even though it's a smaller planet, the ratio of its crust to the rest of its mass is thicker than what Earth's is. It's composed of iron, magnesium, aluminum, calcium, and potassium. Kind of key in on that iron part. When you look at the red planet, one of the things you notice is, well, it's red. That's not a big surprise if you know what's going on in the crust. There's quite a bit of iron constituency. So I'm going to talk a little bit more about why that means that the planet's red, and you can probably figure it out if you've got some background in chemistry. But that's also very important in exploring Mars. Also, the smaller core that Mars has, it's got a greatly reduced mass when compared to Earth's. This is important because it has a huge impact on Mars' magnetic field. At this time, what we can say about Mars's magnetic field is that it's largely not there. There's such a weak magnetic field that it's almost indetectable. So that has a lot of impact on the atmosphere, which in turn has impact on the processes on the surface. So this is also an important part in understanding how to explore Mars. So now that we've taken a look a little bit at the overall picture of the globe of Mars, let's take a look at the periods of its history, how it got to where it is today. There are 4 major periods in Mars's history, each with distinct situations that were going on during those periods. This is very interesting to the Curiosity rover team and the other rover teams who, when they send their rover to a particular feature, it might be exposed from just one point in the history of Mars. So they need to know this about Mars history to interpret what they're looking at and what they can expect to find. This will be important to you because if you're looking at a particular landing site and say you're really interested in finding evidence of water, you'll want to go to an area that has exposed layers that came from a period in Mars history where water would be expected. So to just give you a quick rundown, the first period of Mars history, the pre-Noachian period, which was 4.5 billion years ago, roughly around the same time that Earth formed, that was mostly a period marked by impact events. No surprise. If you know anything about the solar system's history, all of the planets were getting bombarded at that time. In fact, it's called the heavy bombardment period. A lot of the solar system still was filled with debris that had not settled into orbits. And so there was a lot of loose materials going around to smash into moons and planets. So the earliest layer of Mars, the earliest surface layer, there's a lot of enormous craters. The largest craters will come from this period of time. The second period of Mars's history, the Noachian period, which went up to about 3.5 billion years ago, there were still a lot of impacts, although they were starting to get a little smaller. Still large by our standards, but smaller compared to the first period. However, very interesting, water is suspected to have begun to materialize on the surface of Mars at this point. Maybe it was carried there by meteors or comets. Maybe the early chemistry was developing it, but we know water began at this point, not before. The next period was the Hesperian period. That was 3.5 to 2.9 billion years ago. This is a period that we know as the heavy volcanic period. A lot of the large and smooth plains that we see on the surface of Mars formed here. These smooth plains were formed from lava that flowed onto the surface and cooled off quickly, forming a smooth and flat surface. So since the crater period, the biggest crater period was before that, you can imagine that these lava plains formed over craters. So when you're digging down through the history of Mars surface by surface layer, you'll see that in some instances you have a smooth plain that's sitting above water features that's sitting above craters. It's very important when you're trying to find a landing site to know this. Finally, there's the Amazonian period. The Amazonian period lasted from that point to present day. The Amazonian period, there's a lot of features that have formed during this point, including Olympus Mons, the large mountain on Mars you've probably all heard about, largest mountain in our solar system. The lava plain features were still forming, but over time they died down. Water features still are visible in the early part of this time period, but that also slowed down. So this is a period of transition to a more wind, desert-looking world. So here's just a picture of the map of Mars. You've all seen this. I've got site names. I'm not going to go into them in great detail, but I've also got the rover locations overlaid on top of that. You can see that we've sent landers and rovers at a number of places around Mars and in different types of environments. So you can find this online, this information. You can take a look at it. It's useful in knowing where we've already been when you're deciding where you want to land your mission. And also just a simpler map that shows you just the locations of the landers and the rovers. As you can see, most of them are at the equator and going up towards the northern latitudes. Not as much in the southern latitudes. You might keep that in mind. Also, nothing around the area of Olympus Mons. You might keep that in mind. You'll notice the ice caps, we've never sent anything to those. I'll talk more about why that is later. So now I'm going to teach you a little bit about how to interpret potential landing sites based on the detailed satellite photographs that we have from orbit. So this first image, and this set of images comes from the HiRISE image collection. You can look for this online yourself. It's publicly available. You see a crater. I want you to take just a moment and look at this crater and think about what you believe is going on here. I'm going to give you a moment to think about that before I tell you what you can expect here. Okay, so looking at this crater, you'll probably notice that there's trails of debris going in from areas of the crater rim that have been weathered down. And these trails lead down towards the interior of the crater, and you can see what look like sand dunes at the base. You can also see, if you look closely, that there's what looks like dark sand going up to the edges of the crater where those weathered ridges begin. Now, on Earth, we might know what to expect if we saw something like this, but on Mars, it's a little different. First of all, those sand dunes that you see inside this crater, if you were to take a hammer and hit one of those sand dunes, the hammer might break. They're concreted. They're cemented. They're very solid. They're very old. So those aren't sand dunes that are actively blowing in the wind today in the form of powder and that kind of a material. They're cemented with a lot of time spent being hit and hammered by wind features. So if you're interested in understanding the chemical changes that can happen with aeolian or wind processes on the surface of Mars, you might be very interested in the bottom of that crater. You'll also notice that the sand trails going down the edges of the crater, that's also wind pushing the sand into the crater over time. Now those dark trails are actually more recent. Those are fairly new, and you might find more of the fine sand-like material that you're familiar with on Earth there. But the sand dunes, those are not like that. They're going to be cemented. And as far as why you have some darker sand, and then you have the lighter sand, well, that lighter color isn't like on Earth where we have light sand formed from quartz or from coral. This light sand is light because it's the color red. It's rust-type materials. It's oxidized materials of soil that have a lot of iron content. As for the darker sand, that's more basaltic-type material, more similar to the volcano beaches in Hawaii, the black sand beaches there. So that's why you see the different colors. You'll also notice a tiny little crater that's off to the edge of the rim there. That's more recent than the big crater next to it. That's just telling you that there's oftentimes craters that lay on top of other craters. Sometimes you'll look at a feature that looks like it might be a river or an ocean from a long time ago, but it may just be craters on top of craters making very curious features. Now here we have another feature that looks like sand dunes, but if you look closely, you'll notice that not all of the dunes are formed the same way. Now I could throw a lot of geology jargon at you and describe the shapes of these sand dunes, but what's more important is looking at the differences in the different colors. Now this isn't an off-color image, it's not a true color image. However, you are getting a sense of lighter red sand color and darker sand color. Now based on what I told you before, if you think about this for just a moment, you can probably imagine what we're seeing here. We're seeing lighter red sand, some of which is cemented and some of which at the lower left-hand corner is still being stirred up. What looks like actually sand that's being carried in the atmosphere based on suspension. The darker sand dunes, those are more loose sand, and those are composed more of the mix that you have underneath the surface where you've got some basalt-like materials. So when you look at a place like this, you can learn a lot about what's going on with the wind on Mars, quite a bit actually, because you have several features being formed on top of each other. And that sand suspension's a key point as well in understanding current day wind. But if you're looking for something with volcanism, or if you're looking for something water-based, this may not be the landing site for you. Here's a very telling picture. You're looking at what you can tell are stepped ridges that go down into a sandy basin. So I want you to take a moment and think about this picture and decide what you may be looking at. Okay, so already I've given you an idea when you're looking at the red sandy color what that means. And I've given you an idea when you're looking at the darker sand color, the almost black sand color, what you're expecting to see there. You can also expect that when you see these dark sandy features on Mars, you're looking at newer sands. You're looking at newer materials and deposits that have been recently placed, whereas those ridges, you can imagine, especially with the weathered edges on those steps, those are older features. So what you're looking at here, it's actually a very interesting image, and in my research program I looked at a lot of these type of sites. You're looking at an area where over time the ridges and the higher elevation areas were weathered, which is why you have these stepped features on the ridges. But you'll notice that in some instances, especially in the center of the image where you have 2 points of high elevation that weren't weathered down, you see that. And in geology, we know that that means that those areas are far more cemented than the other areas. This is a very key point. When you look at the surface of Mars, don't think about Earth as much. Think about what's going on Mars. When you look at on Earth a riverbed, you expect to see the river dip down like that because water has been eating away at the soil. But think about how long ago it's been since there might have been water on Mars. It's been so long that if you have a dry riverbed like on Earth that hasn't seen water for a very long time, what you know is that the water, as it was going down, as the water was disappearing, it's the center, the bottom of that riverbed received the most exposure to water over time, the most number of millions of years of water running over it. Water is one of the strongest chemical reactants in soil chemistry. Water is a big part, especially with the deposits that water leaves behind, it's a big part of what cements materials together. It's not the only thing that can do that. Wind can too, but water does this consistently. So over time, if you had a dry earth riverbed, the base of the riverbed is the most cemented. The edges on the side, they're going to wear down over time more quickly than the riverbed is going to wear down because those materials didn't get as much water cementing action on them. Eventually they'll eat away entirely. Eventually the riverbed will be at the top, not the bottom. So it turns upside down, it reverses. What you're looking at here is an inside-out feature. The features that are at the highest locations at one point were the lowest locations. They got the most cementing. The areas that were worn down more received less water. But that's not the whole story. Not only do you have an upside-down feature here where the water would have been at the highest locations, but over time, this area was probably covered in wind-blown sand, which then was later excavated again, which is why you have steps rather than a gentle slope on the ridges. After it was excavated, more recently, sand came in and infilled the area. That's that dark sand at the bottom. So you have 3 different periods of time that you can look at here. You can learn a lot about fluvial geology, you can learn a lot about aeolian geology, and you can just learn a lot about what's going on today actively on the surface. This is a great landing site if you're interested in water. Now, some of you may not be interested in water or wind. You might be interested in chemical reactions under the surface. What you're looking at here looks like a bunch of slugs that are crawling through a rocky debris field. It's a very interesting image. I like this one quite a bit. Now, you already have a good idea why you're looking at dark sand poking up from underneath these red rocks. You know that that's more recent sand, and it's got a different kind of content than the red rocky sand does. It's less oxidized. Now, I haven't talked a lot about oxidization, but oxidization, it is what it sounds like. It is a reaction that occurs with exposure to oxygen. That's going to happen a lot more with water and oxygen in the air being exposed to something. So those red rocks, they've spent more time on the surface than these dark sand dunes have. They've spent enough time that whatever oxygen is left in the atmosphere of Mars and whatever water was on the surface of Mars, it worked on those rocks, it oxidized them, they became red and rust-like. That dark sand was lower below all of this. It's basaltic, so it's more of a volcanic type of material. But what you're seeing here isn't related to either one of those. It just tells you why you're seeing two different colors. These areas where the sand has bulged up, and literally has bulged up, these are things that we see today actually actively forming. We don't just see these lying around. We literally can look at satellite images where they aren't there, and then later, a year or two later, we can look at satellite images and then they're there. They're very active features. What's happening here is under the surface, you do have a type of water, or a type of ice rather. You have dry ice underneath the surface with a mix of water included as well. Now we all know that Mars, like Earth, has seasons. We know it's a very cold planet. Sometimes it's warm enough on Mars that Earth has colder spots than Mars does. But mostly Mars is far colder. So things can happen there that they can't happen on Earth. And that includes having dry ice actively present around the planet. You know, we have some of that on Earth, but it's very rare. On Mars, it's a lot more common. You have dry ice under the surface, but when the weather changes and the seasons flip and Mars warms up to a temperature that's actually a little Earth-like, that dry ice sublimes. That's a term for something solid going directly to the gas phase. It doesn't go through the water phase in between. So in your phases of matter, it's skipping a step. It's going directly from solid to gas. But when it does that, as you probably already know, gas exerts a lot of pressure. I won't go into the chemistry behind that, but gas exerts a lot more pressure than a liquid does. So when this dry ice sublimes and turns to gas underground, it's pushing up at the soil. It's trying to escape. It's trying to push out with its gas pressure. That's what's happened here. That's why you have bulges in the sand. That's dry ice that's gone to gas. The gas is pushing up, creating these features, and if you were to look at a place with enough of this, you'll see situations where they will burst. And these look like, and you've probably heard this in the news if you're a big Mars enthusiast, these end up looking like dark spiders that are just sitting on the surface of Mars. Those spiders are actually dark sand that has burst out with the gas because it literally exploded. We call this cryoventing. So if you're interested in cryoventing or cryovolcanism, this image will be something you'll be looking for a lot as far as a landing site. Why would this be interesting? It's an active surface changing feature. So for exploration purposes, this is the kind of thing that a human explorer would have to contend with today. They would literally see this happen around them if they're in this area. So keep that in mind. This final image is less of an interpretation image and more of a fun image. And a lot of people saw this in the news if they're following Mars. That's a twister moving across the Martian surface. Mars does have weather. Mars does have a bit of an atmosphere still and a lot of sand. So not surprisingly, when the winds kick up, it can form the same kind of twisters that you see on Earth. And this is one that was actually caught in satellite imagery. It's the only image we have like this. And a little interesting story, if you've been following the Mars rover Curiosity at one point a couple of years ago actually picked up with a device that can measure wind around it, a circulation of wind that hit it where the winds picked up dramatically and they were circulating in their direction. It passed. There was no damage to the rover, but it's suspected that one of these twisters went right over Curiosity and just ran right into it. But of course, Curiosity is as big as a car and it weighs more than a ton, so it's going to take more than one of these twisters to move it or hurt it. But if you're a human on the surface exploring, or if you design a small rover and send it there, you might want to be aware of this. You might want to avoid some of these large flat plains like this where these twisters can develop. So now that we've done some image interpretation, let's go into the kind of things that can deposit materials here or there on Mars. So how do things just sort of accumulate in one place as opposed to another place? And what processes do that? Well, I've mentioned the word aeolian. Now you can see how it's spelled there if you didn't know about that word before. That's wind processes. So on Mars, what we're looking at is wind cementation, meaning the winds have blown against an area of material for so long that the material gets cemented together. There's wind weathering, which means that the winds have been so strong and they've been working maybe on an edge of a cliff or an edge of a crater that they have torn chunks and weathered chunks out. And that material then gets moved past that point. And then there's dunes. We've seen old dunes that were cemented, but there's new dunes that are actively going on today. There actually are traditional flowing sand dunes on the Mars surface, even though that's not what we've been looking at so far today. There's volcanic deposition. Volcanic, I mentioned before, those lava plains that can come out and form, and then they quickly cool, and then you have a smooth, flat plain that may have covered a previously cratered surface. Important to know about. Volcanic activity, though, can also be responsible for ash that falls from the atmosphere and deposits in a given area. Two forms of deposition. There's fluvial. This form of deposition, which I studied in my Mars research, this is where you have streams that either deposit materials the way rivers and streams on Earth do, or you have water that moved over a riverbed long enough that it cemented the riverbed itself, and over time you get an inverted ridge. That is a river channel that eventually went upside down as the riverbed cemented and the materials around it were weathered away. So sometimes you'll look for this by seeing ridges that look like rivers. So rivers are ridges that are shaped like rivers. Or you'll see deposited materials that are at the edge of what looks like it was a stream. There's lacustrine, a word that we've probably heard less. That's another form of deposition. This is lakes and ponds and bodies of water that don't flow. So Curiosity is actually sitting in a lacustrine feature right now. You'll find small dunes under the surface if you use a rover that can drill. You'll also find large flat deposits, and you'll find cracked mud. So if you dig and drill into an area of the surface and you find cracked mud or small dunes, then you might be in a lacustrine area, and then you can use an instrument to measure the chemistry and confirm that. Another form of deposition, atmospheric dust fall. This is ongoing today. This is where dust that's suspended in the atmosphere eventually has to fall somewhere, and it's evenly distributed across the surface. It doesn't really form in just one spot in one clump. So you can rule out atmospheric dust fall by looking for an organized manner of deposition, and if you see just even distribution of deposition, then you can rule out other features and see that atmospheric dust fall is responsible. Dunes can form as a result of that. That's where a lot of the loose sand is available to the Mars dunes today to be fed into. Finally, there's impact. I don't think I need to say a lot about that. I think you have an idea what craters are and that there's debris that forms at the base of craters and surrounding craters when you have a large impact that slams into the surface. So now that we've looked at deposition, let's look a little bit about mineralogy on Mars, more about what's inside the soil. First of all, I've mentioned that a lot of the Mars soil, especially if it's the redder soil, it's been oxidized, meaning that there's been oxygen exposure to a highly iron content material, and so it has undergone changes, chemical changes. It makes it rust-like. It's not just rust-like, it is rust. That material that you see, that red soil, is actually very dangerous and harmful to human beings. To a rover, not as bad, but it can be problematic to have a metallic rover in the midst of a bunch of rust, as you can imagine. It's slightly alkaline. It's made up largely of magnesium, sodium, potassium, chlorine, as well as iron. And if you're looking at soil composition at Mars and you look around the area of Mars, the whole area of Mars, you will also find evidence that there's possible salt perchlorate traces. It's just a salt that's deposited by water, but obviously for the water enthusiasts, that's something of high interest. So they're looking for that. I've talked about dark sand and how that's similar to the volcano beaches in Hawaii. I've talked a lot about the red color of the sand. And also, another thing is that the red dust that's all over the planet's surface not only has wind circulated around, there's places where it's believed that the water actually created larger swaths of this, or volcanic activity did. There's definitely a large water volcano debate when we're looking at certain features. Be aware of that. If you're looking in an area that looks like it's water or it looks like a volcano, you don't investigate it unless you're prepared that it could be either one, or there's a real open and shut case for one or the other. And we've talked about iron content. Here's some minerals that have been discovered on Mars. We've confirmed them and proven that they are there. Hematite, large deposits of that. That hematite's a big part of the red soil. Magnesium, it's also very common. Found large deposits of olivine. We found a bit of gypsum, some halite and salt, which is very important when you're looking for water. Phyllosilicates, or phyllosilicates, which are also important when you're looking for water. Pyroxenes, feldspars, basalt, of course that's more volcanic, and an extremely rare mineral called titomagnetite. It's just a rare form of magnetite, which is magnetic metal. Now, this is a long list, and some of these words may not mean much to you, but the important thing to focus is that a lot of this is either iron-type minerals or minerals that are made by water. If you're really interested in looking for water, you want to really hone in on this olivine deposits, salts and halites, and the phyllosilicates. So key in on that. We have tested the soil in different places of Mars with rovers. You might look at the areas where we found these things and look at what they're like and look for a similar kind of site if that's what you're looking for. But maybe you're more interested in volcanic features. So you might want to look at areas that look like they have a topography change, where there's a slope and it goes down, so you had an old mountain, or active mountains, and you'll want to look for basalt. So that'll be something to key in for that. I've already talked about some of the environments that those form in, but let's take a look at some specific interesting discoveries on Mars that we found. What you're looking at here are hematite blueberries found near where the Opportunity rover is at. These form in hydrated conditions, and we found them on Earth. So this is something, we have something on Earth that is similar to. We understand what these are. So this is a highly interesting feature if you're just looking for water. Conglomerate rocks. We've discovered this, 2012 by Curiosity. You'll recognize this if you've ever gone fishing at a lake or swimming in a pond. These type of rocky, clusters of materials that have been cemented together, these are very common where you have riverbeds or stream beds, flowing, moving water. And not just flowing, moving water, but quickly flowing water, fast-moving rivers. We've also seen clays and hydrated materials. Curiosity found this in 2013. And you're looking at some pictures of that Curiosity snapped. Now, you may not be able to see it very clearly, but in that gray photo, there's a color code that's helping you to see the specific minerals. So clay, again, something that you look for with water formation. Mudstones. I mentioned before that cracked mud is a very key feature when you're looking for lake deposits. Curiosity has found that. Curiosity has gone around, it's drilled, it's looked at exposed features, and it has found mudstones. And that has told us that at least one area that Curiosity has been at was a large lake. Here's a picture where you can see that lake in relation to the overall crater that Curiosity has been exploring. It's very interesting. Also, and this is the most recent Mars discovery, methane gas and organic materials. This was discovered last month. This is very, very new and very exciting. Curiosity found this at the Cumberland site in Gale Crater. It used the tunable laser spectrometer after it used its drilling device. And literally, after drilling, there was an explosion of methane gas that came up. Now I say explosion, it's very small, but it was methane gas, and methane gas has been hard to find on the surface of Mars. And that forms usually either as a result of water or life, so either way it's an exciting find. But also organic materials were detected. Don't know what kind, but they were detected. And here is an image of that device. I thought you might find this interesting in case you want to have a similar spectrometer on your own mission. Future missions that have been planned, these are actually very exciting. In 2016, the InSight mission is prepared to launch a geophysical monitoring station. For the first time, we will have a seismometer on Mars. It will be able to deploy a 16-foot deep heat flow probe that will drill down into the Mars surface. If there's any earthquakes on Mars, we will know. We will also learn exactly how dense that core mantle are, what they're made out of, and just any kind of seismological activity on the planet, we'll get that information. So it's a very exciting mission. And then there's the 2020 rover. It's going to have a very sophisticated organic chemistry lab apparatus on it. So a lot of what Curiosity has been able to do, this rover will do it and do deeper investigations. So instead of finding out that there's organic materials, we'll know exactly what kind of organic materials and if those organic materials must arise from life. That's a very exciting mission as well. So that's it for my slides. I'm now prepared to take questions that you may have.
All right, folks, so the way we're going to do questions is if you want to go ahead and prep those questions in your chat window, do not press enter just yet. What we'll do is I'll go ahead and call on you, and then when your name is called, you can go ahead and click enter, and your question obviously will pop up into the chat window. So go ahead and raise your hand. The hand icon is just underneath your name, and that will let me know that you have a question that you want to ask Aaron, and then we'll go ahead and take those as they come in. So we'll go with Clayton Palmer first, and then we'll go over to Goodson next. So Clayton, go ahead and type in your question and submit it to the chat window, and then Goodson, get your question ready to go, and Bree, you'll be up after that. Okay, it looks like Clayton's having some issues right now. So Goodson, if you're ready to go, you can go ahead and submit your question. We'll come back to Clayton in just a second. There you go. You want me to do that? Okay, so the question is, what is the most unactive, flat, boring geological area you know of? So we'll go ahead and let Aaron tackle that one.
All right, great. So you're not interested in water, but wind and large areas of flat land with low geological features. So if that's the case, then what you're probably going to be interested in the most, just take a look at this picture we've got on the screen right now. There's a reason that speculative artists have put an ocean on the top half of Mars there. A lot of the northern areas of Mars are smooth, flat plains. We don't know if there was volcanoes or oceans or what up there yet. We've got plenty of evidence going in many different directions. But it's a very smooth, flat plain. In fact, the Viking landers were targeting this area because it's a safe landing site. And because it's a safe landing site, you can design a cheaper mission if you do a landing there. You don't have to worry as much about competing with ridges or mountains or hills. And you should see wind phenomenon there. But keep in mind that a lot of that area is smooth and flat, and you won't get to see wind and weather erosion. Now, if you want to see wind and weather erosion, then I might recommend what's called Terra Meridiani. Terra Meridiani is it's close to the equator of Mars. So if you actually went to the not just the equator but the prime meridian, so if you looked at like literally the center point of every map of Mars, you're pretty close to Terra Meridiani. That's why it's got the name Meridiani. That would be a good spot to look for a lot of wind features that are actively shaping the surface, as far as ridges, things like that, dunes. But if you're just looking for a large flat plain, you can't get much better than the top.
Okay, we got a question from Clayton Palmer here. It's a rather long question here, so I'm going to let you kind of scan that. And then Bree, you'll be up next. And then we'll go to John Paul after that.
Okay, so where are the best locations to get some of the most commonly used and readily available alternative surface level constituents for making cement? So making cement, so looking for calcined lime and clays. Okay, so if you're looking for the kind of materials you need for that, you'll want to look for lake beds and river beds. Lake beds, go to craters. Not just any crater, but you want to look for craters I'm a little biased, but more of the craters that we've seen that look like they might have had water in them occur along the equator or to the south of the equator. So I would look for craters that are in that vicinity for your lake deposits. You'll get some things there for clays. But for the cement, you need areas that had channels, river or stream bed channels specifically. You can get some things from wind features, but it's kind of tough to predict exactly where that's going to be. You can look for some craters that have cemented sand dunes for aeolian cement, but if you're looking for river and stream bed, go to the equator. You can go in either direction, but you're going to find some higher elevation surface that's going quickly to lower elevation surface, so some sharp declines. There's a lot of evidence that rivers or streams might have flowed down those declines. So I would look to that area of Mars, and again, when you design these missions and these lander missions, make sure that you think about how safe it is to land in a given area. You need a flat area somewhere to land. So if you're looking at areas with hills and sharp elevation change, you need to find some spot where it's not quite as sharp, where it's a little bit more gradual. So that would be my recommendation.
Okay, so we're going on to Bree's question next. Can Mars' atmosphere environment be manipulated to where it can be more favorable by geoengineering?
So I'm going to assume that this question, when you're talking about the atmosphere of Mars and favorable to geoengineering, I'm going to assume you're thinking about geoengineering in terms of terraforming, making the planet more habitable to human beings and human activities on the planet. If I'm accurately understanding the question, the atmosphere of Mars as it is today is not favorable for that kind of a thing. We would have to do a lot to the atmosphere. Now, we're learning a lot about the atmosphere now because we have a new satellite in orbit around Mars that's specifically sniffing the atmosphere. So we're learning a lot right now about the history of the atmosphere and the present day atmosphere, but it's very thin and it doesn't have what we need. We'd have to introduce a lot, and we'd have to create some large-scale chain reactions in the atmosphere to terraform and geoengineer it that way.
And just remember, folks, if you want to go ahead and ask a question, you want to go ahead and raise your hand. We're going to call them in order on which they were received. And the way you do that is you prep that in the chat window, and then when I call on you, you'll go ahead and submit that. So John Paul is going to be up next.
Is that that?
Yeah, and so this question is how do you age Mars?
How do you age Mars? Okay, so how do you determine the age of Mars? Well, since a lot of the exploration of Mars started with more rudimentary technology compared to what we could do here on Earth, we had to use Earth analogs, as it's called, things on Earth that we can compare to things on Mars for a lot of the dating. The solar system has largely been dated based on chemical analysis of meteors, cometary materials, things that we can collect actually from space. The office that I interned for, Ares, they actually have a lab where they look at materials that NASA has collected from outer space, and then we have dated them. Things like the dust in the comet trails, things like meteorites, meteors, asteroids, moon dust. So we've done aging on these things. We've done aging on Mars, but when you're looking at the features on Mars and trying to determine their age, we take the 4.5 billion years that we get for the age of the solar system, and then we look at how long it would take certain features on Mars to form. And we also look at what was going on in the solar system at different points. The heavy bombardment period, we already know when that was. So when we look at the largest craters and where there's a ton of craters, we know more or less what period of time that was. But after that, we're using Earth as a way to estimate how long these features would form on Mars.
Okay, next up is it's NDEDR Dartham. Okay. Yeah, so a question about Mars and rotation on its axis.
Okay, so there's a difference between gravity and electromagnetism. And I've done some research in electromagnetism, so I've actually had to really look closely at this. It is the gravity of Mars that attracts moons, which has to do with mass. Anything that has matter and mass exerts a gravitational pull. There's a lot we don't know about gravity. That's high-level physics. But we know that anything with mass attracts other objects to it, and the greater the mass, the greater the attraction, which is why the sun has such a powerful gravitational field. It's got all these planets orbiting it. Something like Mars, which is a bit smaller, the best it can hang on to is Phobos, that little moon that's got going around it. Nothing like the moon that Earth has been able to capture. So that's where the moon comes in. Now, as far as the tilt, the axis, keep in mind that the movement of the bodies of the solar system has a lot to do with the sun's gravity and the sun's pull on these planets. So when the sun collects and captures objects in the solar system, and then they get captured and orbit around it, they start going into centripetal and centrifugal forces, which is a big part of the spin that these objects have. So when you're talking about the axis, you're talking about the spin. Now, I understand that you think of axis and magnetic field together because the magnetic field is largely generated based on the direction of the axis of a given planet. But the magnetic field also is generated by convecting metallic core, because anytime you have something with an electrical charge that moves, you have a magnetic field. So you have to have that motion. Mars had one, a magnetic field that is, because it has a core with metallic materials moving. But because the mantle is cooled down and it doesn't have that convection, and the core has less convection than Earth does, and all of it's much smaller than Earth, it's just not enough to give Mars much of a magnetic field anymore.
So Laramie, you're up next, followed by Natasha and Grant.
All right. With the, let's see, PowerPoint. Is it this bottom question here?
Correct. Yeah. Well, the PowerPoint we post online, where can I find the photos of Olympus Mons?
Will you have the PowerPoint posted somewhere?
There'll be a recording of the event.
Yeah, we're going to work this, so they can see the
okay, so yeah, you'll be able to access the PowerPoint and the recording later. And as far as good photos of Olympus Mons, the images that I showed during the presentation, the HiRISE, H-I, RISE, R-I-S-E, all one word. Just Google that, and you can get images of most of the planet. You can definitely get very, very good images of Olympus Mons. So just there's publicly available satellite data that NASA has put out there. You can definitely get these pictures of Olympus Mons in the kind of detail I showed. Keep in mind it's going to be very zoomed in, so it won't be like the grand view that like we would look at Mount Everest with.
All right, Natasha, you're up next, followed by Grant. So how would the volcanoes on Mars work differently than the volcanoes on Earth work today?
And how can one study geophysics and volcanoes? Okay, all right, so you got two questions. I'll answer those. Difference between volcanoes and Mars, which there are none anymore, so that's one key point, at least none that we can prove. How are they different from Earth? So for starters, Earth's volcanoes are often resulting from very, very huge mantle plumes that come from the mantle, and they're coming up to the surface. We know that Mars mostly has a dead mantle now. We really don't know how active that mantle was in the past. If that mantle wasn't very active, then that means that the volcanic activity would have been very sporadic. It wouldn't have been very frequently that you'd have a volcanic eruption. That's one difference. As far as how big or small a volcano can be, it'd be about the same as on Earth, because that has more to do with how much magma collects in a given spot under the surface, not necessarily how much of a mantle you have. But how commonly eruptions would occur, that would relate to how thick the mantle is. And for Mars, probably there wasn't probably a period where volcanism was as common there as it ever has been on Earth. And that period of time when there was volcanism was billions of years ago, as far as we can tell today. Today we can see what may be ice volcanoes, cryoventing, and there's actually some research out there that maybe there's mud volcanoes on there today. We haven't proven that, but there's some suspicions about mud volcanoes too. But that's a little different from magma volcanoes. As far as where you can study volcanism and geophysics, California has a lot of emphasis on that. Arizona does, so look at schools there. But really, you can find geology programs across the country that will study volcanism. So I wouldn't want to limit you to those two, but I know for a fact there's a lot there.
All right, Grant, you're up next, followed by Art Smith, and then Chandra. Here's Grant's question.
Okay. Let me see. Okay, so we got several questions, and I think I can tackle these. One of the questions is the North Pole, or the ice cap on the North Pole, is it pure water ice, or is the ice mixed with soil? Actually, the North Pole is a very thick ice cap there. It's not pure water ice, but you do have pure water ice. It's two layers of ice. You have dry ice layer, and you have a pure water ice layer. The seasons on Mars are such that there's times during the year when Mars warms up, and when it warms up, that dry ice doesn't stay in its solid form. I told you before, it sublimes. If it's dry ice, it goes straight to gas, skips the liquid phase. So it doesn't exactly turn to gas and then fall back in the form of snow, but it can form snow. Snow can form from dry ice. So you have dry ice becoming gas, it suspends there, it can form snow. We see a lot more of the snow in the southern ice cap, and yes, there is snow there. But that's not water ice snow, so keep that in mind. The water ice cap, it doesn't melt. It stays solid. It's just so cold that it can't transition. And let's see, did I capture all of that question? Yeah, I think I caught that, yes.
All right, Art, you're up next. So a question about mission maps when it comes to Mars landings.
Maps to show
Latitudes and longitude coordinates. Where can they find those?
Okay. For landing sites, one thing that you should probably keep in mind with rovers, with landers don't move, they just land and then they sit stationary. But with rovers move very, very slowly. I don't know how many of you watched the Big Bang Theory TV show, but they had a funny episode where a character took a Mars rover replica to a baseball game to throw the first pitch, and the rover never made it to home plate, because that's how slow the rovers move. So as far as the area they cover, it takes years for them to get very far, and when we say very far, we're not talking far in terms of like Earth distances. So maps of those areas, they are available online, but they're broken up. The best maps are probably from the research teams. They tend to hang on to that. You'll probably want to go to Google Scholar and do a search on published research papers on Mars from the mission teams. Some of those may have paywalls, so just be patient. It's going to be a bit of an effort. But you can find just maps available by NASA and other groups that just give you an idea how far from the landing sites those missions have explored. It's not very far. So really, if you can kind of stay away from a landing site by a good 50 miles or so, then you're going to have area that hasn't been covered. And since we've only had a few landings in our history on Mars, it won't be hard to avoid those landing sites.
Okay, Sandra, you're up next, followed by Katja and then Jackie. Okay, yes, that's a great question. A couple of questions there. Okay, the poles. I said I would talk a little bit more about the poles and about why that's been a no-go zone. First of all, I've already mentioned that you have in the North Pole specifically, a water ice cap and a dry ice cap. And the dry ice cap, based on the seasons, it sublimes and becomes gas very quickly and not gently. If you have a rover running around that area, you got to be careful because the terrain changes. Earlier someone asked if the soil was mixed up with the ice. Absolutely, soil gets mixed up with the ice because you have wind blowing the soil around the whole planet. So you have a lot of changes in the landscape that occur, but it's so cold on these ice caps. We just can't design a rover that's within a reasonable budget that can survive in these temperatures. I mean, you could design something that could survive it. It's going to be very expensive. I mean, if we sent something that could last on Venus for 20 minutes, we could send something to the Mars ice caps. But it's going to be very expensive,
And the budget for space missions these days, it's just a different picture, and you've got to get your rover to be $2.5 billion or less, and that's pushing it. You know, usually if you can get it 500 million to $1 billion, you're pretty good. You're not landing on the ice caps in that budget. So.
All right, Cocktail, you're up next, and then Jackie, and then Jimmy will be after that.
Okay.
Hold on, there we go.
Okay. The Phoenix Lander, if you've heard of the Phoenix Lander, was a lander that landed as close to the ice cap, the northern ice cap, as we've ever been. It couldn't get into the ice cap itself. All it could do was get close. Again, it's very cold up there. The hope was that the Phoenix Lander would be able to actually get good testing done of the ice to really confirm that the kind of ice that's there. And so the Phoenix Lander arrived, and there definitely was ice. We gained a lot of information from that mission, but again, it was at the edge of the ice cap. There's a lot about that ice cap we didn't get to learn from the Phoenix Lander, and we still can't because it's just so expensive to design a lander that can go there. If you send a rover there, you definitely can't rely on solar power anymore. You're looking at a nuclear battery like Curiosity has. But as far as the instrumentation, MRI instruments, magnetic resonance imaging, I don't believe the rovers have MRI scanners on them, but we've done magnetic imaging from the orbit. So putting that on a rover might be a good idea, but I don't know off the top of my head how expensive that would be and if it fit your budget.
All right, Jackie, you're up next.
All right. Okay. There's a number of different things that can cause methane, but mostly it's a result of either water moving through silicate materials. For instance, an olivine deposit, if water moves through that, you might have some methane created, or biological organisms. To confirm that, you'd need to be able to pick up how much methane, what is the activity of the methane. If the methane is based on seasons, then either there's water that's undergoing rapid changes during those seasons, or you have seasons where there's more organisms that are developing and proliferating. You also have to be able to use instruments that can do chemical tests of that methane. We haven't detected methane anywhere else on the surface of Mars besides where Curiosity is at. Curiosity took a long time to even find methane, and it wasn't much. It had to drill to get there. We have detected, or at least it's believed to have been detected, methane from the atmosphere. And actually the European Space Agency got a reading that everyone has been excited about. There was a spike in methane that it picked up in the atmosphere for a brief period of time at one point with one of its satellites. And there's been a chase ever since to find it on the surface somewhere, because that spike would be more likely biological in nature. Though it could be geological, the biological source would be more likely. So the 2020 rover should give us better readings on methane if it can find it, but again, it's been tough to find.
Okay, we got time for one more question. Jimmy, if you want to go ahead and ask your question. Your plans to visit the deepest parts of Valles Marineris, and do we have an idea of what could be there? Okay, the way that NASA works when it's sending missions to Mars, and not just NASA but other space agencies, is there's usually a competition between different research teams that come up with their proposals, much like you're coming up with proposals. They come up with budgets, what can they learn, how valuable is that data, how much research for how many years can you get out of it, and NASA has to pick between these research team ideas. You put a rover together, you're usually putting a suite of instruments together on it, each of which are completely different in their purpose and have different research teams working with those different parts of that one rover. So that's usually what comes together. There may be hundreds of research proposals. There have been research proposals for Valles Marineris. Nothing confirmed or approved, and as far as I'm aware, nothing that looks like it's going to be getting into launch mode anytime soon. But if you don't know what Valles Marineris it's the largest valley on Mars. It's an enormous canyon, and it would be very interesting to study. Keep in mind it's also very dangerous to land there. It is a canyon. So as far as what could be there, you could find a lot of weathered materials, and you could learn about the weathering processes. That might be water, wind, volcanic. Anything goes in Valles Marineris because we really don't know much about what formed it in the first place. All right, so it's 5 o'clock now. We're going to go ahead and wrap things up. Aaron has agreed to stay for a few minutes, so we'll probably take the next maybe 3 to 5 questions that we still have in the queue here. And we want to go ahead and thank you guys for joining us. Please continue to work on your course online, and obviously your final project responsibilities and activities. The final project due date is coming up pretty fast and furious here, so we encourage you guys to reach out to your instructional assistants if you have any questions, and continue the good work that you've put in so far. We do want to remind you that next Monday, which I think is January 26th, we're going to be having our 3rd subject matter expert presentation about the Mars Science Laboratory and the Curiosity rover from Dr. Ashwin Vasaveda out of the Jet Propulsion Lab, so he'll be joining us then. We want to encourage you guys to attend again, and obviously come prepared with some questions to ask Dr. Vasaveda about his work. But saying that, I'm going to go ahead and see if Kathy has anything else that she would like to say before we wrap things up. And then, like I said, Aaron has agreed to take a few more questions after we officially close out the session here.
Just want to thank Aaron for a fascinating presentation. This was just excellent, and thank you to all the students for your wonderful questions. It's really exciting to see the curiosity and to hear some of the answers that Aaron was able to provide, and the images were just fantastic. Thank you so much for taking your time and sharing your expertise with us.
Thank you.
All right, so we're going to go ahead and just do a couple more questions. Heidi, you're up next, and then we'll go to Aaron. And we'll only have time for about 3 or 5 more questions. So there's Heidi's question.
Okay. Interested in water and microbial life. Recommend land towards the northern area. Okay. Water and microbial life. So the northern area of Mars, I didn't talk a whole lot about this, but Borealis Vistus, the northern surface that's all smoothed out, a lot of people think it used to be a big ocean. Some people think it used to be a gigantic volcano plane that was formed either from a major impact or a supervolcano. Not really sure. But either way, whether it was an ocean or volcano plane or an impact plane, not really a great place to look for water and microbial life right now. Water, if it still exists on the surface or on Mars today, would be underground, and it would probably be in areas where you had a lot of drainage, where the atmosphere would drop water and the water would collect more in a given area. The large flat plain is not really good for that, so I wouldn't really recommend the northern area. And for microbial life, you want to look for a lot of chemistry, so you need an area that's got a rich diversity of minerals. And certain minerals might be better. If you look for clays, and if you look for olivines, and you look for muddy type materials, this is probably a better place to look for microbial life. I recommend, rather than looking at the northern half of the planet, again, look down the equator. Look for a lot of these areas that have topography changes along the equator. That's what I would recommend.
All right, Aaron, you're up next.
Okay, water ice on the North Pole, is there a reason that it would not be useful as a resource for human beings, especially for fuel? Would deep drilling be feasible? Deep drilling, okay, so if you've studied some of these really fantastic Antarctica ice missions that Russia and the United States and several other countries have been doing, where they're trying to get to the deep lakes below the ice, so that they can test and see what it's like in places that have been separated from the rest of the world for millions of years. It's not easy to drill that deep through ice. It's very difficult. It's hard on the equipment. And here, we're trying to send the equipment to another planet. That's expensive, and the heavier the payload, the more difficult it is to get it across space and get it to land. So if humans already have a presence on the planet Mars, then it's probably easier to conduct such missions, but we'd need to get a lot of setup first to do that. Just drilling would be very tough, so could it be done? Yes, probably more like something that we'd see in 150 to 250 years from now.
All right, Michael, you're up next.
Okay. Where would you want to set up something underground for storage, shelter, and launch facility? It'd just be the same as Earth. You'd want a place that has that you're not on solid bedrock, so you should have enough loose soil that you can dig through. But you want to get some foundations in somewhere. Probably again, the equator would be a good place. Look for somewhere on the equator that's a little bit flatter. That would be my recommendation. Arabia Terra, that might be an area that's actually bordering that ocean-like feature on the northern part of the planet. It's above the opportunity exploration area. And as far as seismograph, I don't really have a good timetable for you, but I do know that next year we'll start to hear a lot about that mission. We'll get some better details.
All right, Jessica's up next, and then we're going to have wrap it up with the last question from Michelle.
Okay, landing your twisters won't be a really big problem for the landing equipment because it's all going to be heavy enough that these kind of twisters won't be a problem. We're not talking about scale 5 tornadoes on the planet Mars. We're talking about dust devils, as you would call them in Texas or Arizona. We're talking about smaller things. They're more a problem for the sensitive instruments of a small rover. For a human being, it could be troublesome, but we're not talking killer tornadoes here. So I wouldn't worry too much about that. But if you're going to set up a colony and you're going to have, like, say, tents, you might want to avoid large flat plains. That's my best recommendation there. As far as the red soil, I thought I covered that, but just to go into the effects on humans, we're talking about rust. Basically, think about how we are with rust. It's very, very, very toxic to humans. That can't get in your suit, your spacesuit. You can't breathe it. You can't get it in your food. You can't get it in your water. It's toxic on every level, and since the whole planet's covered with it, any missions to Mars, you really have to make sure you quarantine the humans from the rust.
All right, and the final question is from Michelle.
Oh, great question. Fantastic. Well, you'll be having some of the same professors I did, Michelle, because I was in the physics program and in some of the engineering physics classes. As far as planning a career and looking at what kind of drilling on Mars is feasible in the very near future, InSight, that landing mission is a good preview of that. We're talking very, very lightweight probes that can get through looser soil and go maybe anywhere from a few feet to 16 to 20 feet underground in loose soil. We're not talking about heavy drilling through bedrock. We can't really get to that point just yet. That's pretty heavy machinery, and it costs a lot of money to send heavy objects to the planet. But I think probably in the next 30 to 70 years, we might have some heavier drilling equipment up there to where you could probably get 20 feet into something that's rockier. So that's the kind of drilling I expect that we'll be going into.
All right, folks, thank you for joining us. We hope that you'll come back on Monday and participate again. Have a good night.